You can call it Introduction to Electrostatics. So here we will not be talking about current part, but we'll be talking about the static part. The first thing, what is charge? We have got positive charges like protons, negative charges like electrons. Positive charges could be ions also, like sodium plus ion, calcium plus ion, and likewise negative charges can be ions also. In fact, in a real situation, getting proton as source of positive charges in isolated form is extremely difficult. Getting protons in isolated forms is extremely difficult, except one case where you take hydrogen atom and you take its electron out. So hydrogen atom without electron is a proton. But otherwise, if you take any other atom and you imagine that you would take protons as the sources of isolated sources of positive charges, that's really difficult. That takes us into the nuclear world, basically, nuclear physics world. So for our day-to-day life, when we deal with positive charges, often we are dealing with ions. Electrons as negative charges is a very practical situation for day-to-day life also, because removing electron from atom is quite easy job to do. In fact, the electricity that you are having is possible because of the nature of electrons, or at least some of the electrons, that they are loosely bound and they can be taken out. Electrostatics is very much like gravitation topic of mechanics. There is one difference though, that in gravitation you could only have attraction, and here you could have repulsion also. So you had only one type of mass, call it positive mass if you like. Here you don't have one type of charge. You have got two types, positive and negative. So then like charges repel, opposite charges attract. This thing becomes specific to electrostatics. And it was only attraction in case of gravitation. But otherwise you will see a lot of synergy in the formulae. And gravitational field is conservative field. That is, work done in a closed path is 0. Later on when we talk about electric field, then also it's the same story. It is a conservative field in electrostatics, of course. So work done in a closed path is 0 for electrostatics electric field. If you take equal number of positive and negative charges, then effectively there is no charge, neutral. That's the case with atoms. If you talk about atom, then positive charges live in a very small region, a region of the order of Fermi meters, a region of the order of Fermi meters. What is Fermi meter? 10 to the power minus 15 meters. In that small region, all positive charges live. And within 10 to the power minus 10 meter range, you find all electrons distributed. Within such a small 10 to the power minus 15 meter radius, positive charges which repel each other, they live together. Now that's possible because of some other force. What is that force? Responsible for keeping enemies together. Name of that force that binds protons and neutrons within the nucleus.
So electrostatic forces?
That is a repulsion. Electrostatic nuclear. Right.
Sir, nuclear force?
That's correct. Nuclear force. So if nuclear force were not there, nobody would have lived, basically. Nobody. No atom would live. If atom cannot live, molecule cannot live. If molecule cannot live, plants, lives cannot live. So that's about charge. Fundamental sources could be electrons and protons, but for positive charges, we normally deal with ions in our day-to-day life. Now, when I say fundamental charges, I'm really not getting into the further details. You must be aware that even the particles that were thought of as fundamental particles, even those are broken down further and further. And one really doesn't know up to where the story will go. You keep on breaking particles more and more and more. So for our purpose, when we would say that what is the minimum negative charge, then the answer should be the charge of electron. Even though you may be aware that it is possible to get 1/3 or whatever, 2/3, your answer should be electron only. That is minus 1.6 into 10 to the power minus 19 Coulomb. Okay? But this world of physics is very fascinating, of getting more and more and more, breaking the particles further and further and further. Now, conductors and insulators. What's the difference? The difference is that in one case, electrons are free to come out, and in the other case, they are not free to come out. The job of an electron normally is to revolve around the nucleus, right? That's what happens in case of insulators. Electron does its job, revolves around nucleus. All electrons do this job throughout the insulator. They don't come out. But in case of conductors, some of them manage to become liberated. They become free. And they can travel long distances. So just this word free makes all the difference. You have got free electrons in case of conductors. You do not have free electrons in case of insulators. So if electron can become free, then it means that when it leaves the atom, then that atom would become an ion. So if you look at a typical metal wire, a typical metal piece if you take, whether it is connected to battery or not, it doesn't matter. Inside that metal wire or piece, if you could see actually, then you would find a lot of ions are there and electrons are just going here and there. Free electrons are going here and there. Not all electrons are free. Not all electrons are free. I am not talking about something like plasma. Most electrons are revolving around the nuclei, most of them. Some electrons become free, say 1 per atom or 2 per atom, that way. So only those are called free electrons. But in case of insulators, no chance. Now, imagine some metal ball, and that ball has got negative charge. What does it mean? It means it has got more electrons, excess electrons. Now in that figure, that girl is touching that ball, and look at her hair. So electrons are moving with moving and reaching here, moving in various parts of the body, including the hand, fingers, everywhere. Reaching here also, and if various hair strands have got electrons, then they have got net negative charge. A hair strand is supposed to be electrically neutral otherwise. But because of these extra electrons, that each hair strand has become negatively charged. And negative charges repel each other. That's why it happens. Each hair strand is trying to run away from its neighbor. We have talked about the origin. Origin is electron, proton. Origin of charge, then getting the charge. That includes ions, electrons, both. How does one separate charge? How does one separate charge? My body, say, is electrically neutral. An atom is electrically neutral, molecule is electrically neutral, so a body which is made of large number of molecules, that is electrically neutral. But sometimes when I touch a metal door, I feel shock. So that means sometimes it does happen that the body which is supposed to be neutral is not neutral. And that's why when a metal object is touched, there is a sensation of shock. Shock simply means electrons are moving, and that I don't enjoy much when electrons move. That's the feeling of shock. So it is possible that a neutral body can acquire a net either positive or negative charge. So how do we separate charges? A body is neutral only because positive charges, total of positive charges is equal to the total of negative charges. Say 50-50. If it is 50-48, you have got charge. If it is 50-52, you have got charge. There are various ways to do that. Friction. That man is walking, say, on some carpet, and his body is neutral in the beginning. In the beginning, his body is neutral, but he is walking over carpet. When he walks, you are able to walk because of friction. So when he walks, there is some friction acting between the bottom of his shoes and the carpet. Now when there is such rubbing involved, electrons can jump from one to the other, say from either way, carpet to the shoes or shoes to the carpet. There's a possibility, right? So that person may be electrically neutral in the beginning, but the moment he reaches the metal, he reaches the door has got a metal knob that you see in the drawing, in the figure. That knob is metallic. So he touches that knob to open the door. And the moment he does, he experiences shock. It happens, it's very much practical. I have experienced this type of thing many times. So why would that happen? Because when the person walks, body has got some net charge. That doorknob is metallic. Metallic means it has got free electrons. It has got free electrons. That's very important. If that person touches wood, in that case, electrons inside the wood won't move easily to the person's towards the person's hand. They won't move just like that. But here, metal, free electrons can easily move. So when electrons travel through the fingers, that doesn't give a very nice feeling. It may not be much. That's the difference between a shock of when you have high voltage, say 220 volts, that shock versus this shock. That they are very much different from each other. This is the shock of electrostatics type. This is the shock of electrostatics type. This one. And that one 220 volt supply, that shock is of much greater magnitude. So we are talking about this type of shock, electrostatics. Now this can be big also, provided the charge transfer is big. But normally in day-to-day work, walking over carpet or wearing woolen clothes or wearing certain types of shoes, these types of activities do not involve such a huge amount of charge. So that's why it is not that much. So due to friction, one can get charge. You know that typical example of Coulomb lifting a small piece of paper, but it just doesn't work straight away. You comb your hair with it. You take a comb and you comb your hair, and then it works. Rubbing. Comb rubs hair. So friction is involved, and then that typical example of balloon. Rub balloon with your hair, and then you find that balloon is able to stick to a vertical wall. Friction, friction, friction everywhere. So now balloon won't just hang, but after rubbing it is able to hang. So balloon was neutral earlier, and after rubbing it is no longer neutral. So you are able to separate charge. And now it is not neutral, and it is able to hang on a vertical wall. So friction, lots of examples. Now in friction there is contact, there is rubbing, right? Conduction does not require rubbing. Conduction does not require rubbing. So that example that we saw earlier, one girl touching that globe and her hair becoming straight, in that there is no rubbing involved. So that ball had some charge already, and when hand was kept on that, then charge moved. No rubbing involved. So that is conduction. In case of friction, one body doesn't have to be charged necessarily. In case of conduction, one body has to be charged necessarily. That ball was charged. So the girl's body got charged because that ball was charged, that metal ball was charged. It's not that it was neutral. But in case of friction, you do not require one of them to be charged. In case of this example of ball and the girl, if the ball had negative charge, the girl would also have negative charge. If the ball had positive charge, the girl would have positive charge also. Can you imagine why should the girl have positive charge if that ball has positive charge, knowing that positive charge cannot flow? Ions cannot move on your finger. Ions cannot move on a ball. Positive ions cannot move. Ions generally cannot move unless you have got a liquid, either aqueous solution or liquid state. Ions cannot move. So if the ball is positive, the girl acquires positive charge. How is it possible if positive charge cannot move? Any idea?
So flow of electrons from that body to the metallic ball.
Perfect. From her body, electrons jumped to that ball. So one can get positive charge by losing electrons. One doesn't normally get positive charge because positive ions have jumped in. That's very rare. And protons jumping, forget about it. Now, whether we talk of friction or we talk of conduction, contact is involved, physical contact. In case of induction, no contact is necessary. Then how does induction work? Let's see. This is a metal ball. This rod has got positive charge. It's not going to touch the ball. It's not going to touch the ball. It's just close. That's it. Now this is metal, and that's very important because we want free electrons. So the free electrons would be interested in positive charge. So they would come close towards this side. So the density wise, if you see, the density of negative is increasing here. That means the density of negative must be decreasing this side. So you have succeeded in separating sort of positive and negative, though you have not really given this body a net charge. Okay, minus and plus, there is some separation, but net charge still 0. Job is not done yet in totality. So one more process is required, and that is connecting the distant side to the ground. Connect this side to the ground. Now what happens that these electrons are locked, so to say, by these fellows. These fellows are not letting them go anywhere. Whereas ground has got huge supply of both types of charges. So the electrons which are here, they are interested in these positive charges. And electrons go neutralize. All these 6 positives become 0, 0, 0, 0, 0. Now you have got a net charge. So this fellow which was neutral initially, now it has got a net negative charge. Without grounding, you can only separate charges. And sometimes we use induction word just for that. But the whole process of giving charge by induction process, the whole process must include grounding, without which you cannot give net charge. And it will always be opposite. If this was plus, this would be minus. Always opposite. So in case of conduction, same. In case of induction, opposite. And in case of induction, no physical contact required. Any questions? Let me know. Very well. So try to answer this question. A negatively charged rod is used to charge an electroscope by induction. Let me just say metal ball. A negatively charged rod is used to charge a metal ball by induction. What is the resulting net charge on the metal ball? Positive, negative, or 0?
The positive.
So 0.
0.
So positive.
It should be positive. Positive. If this is negative, then what will happen? What do you think? What will happen now? Who will come here?
The positive charges
So
will accumulate on that side.
The positive charge.
Okay, now if you...
protons will come here.
Protons will come here. Well, proton cannot come. And those who think positive charge can come, can you explain how positive charge can come? Because protons cannot move, ions cannot move. And how positive charge will come here?
So electron will repel from that place.
Perfect. That's the correct answer. This is a metal ball. It has got electrons. Electrons will feel repulsion. They will run away. So electron density increases in this region, and therefore electron density decreases in this region. And then when we ground this, then what do you think will happen? Will positive charges go from the earth? Or will electrons travel from here? What should actually happen?
So electrons will go towards the ground.
Correct. So these electrons go towards the ground. Ground can accept as many electrons because it is simply massive. It's like a sea. You are giving a bucket of water to sea, nothing. Doesn't matter anything. So these electrons will go to the ground. The result? Positive charge. So the answer to the question is positive charge. Any questions? Let me know. All right, then let me give you one more question to think. If the metal ball was replaced by an insulating ball and then charged by induction, as we have discussed, what would be the net charge on the ball? Positive, negative, zero. We have got an insulating ball in place of zero.
So it must be zero.
And why should it be zero?
As electrons do not
are
move.
here not free for to move.
There are no free electrons. There are no free electrons. So if you do this type of thing, and this fellow has got no free electrons, then how can this minus plus happen? Who will get repelled? Who will get repelled? Even separation will not take place. This thing itself won't work. So the result is nothing, 0. Any questions? Let me know. This ellipse is here. We need to do some math now. Between 2 point charges, this is the force. It follows inverse square rule, just like gravitation. The difference is that it can be both attractive and repulsive. Difference with gravitational force. One more difference is that of the constant. In case of gravitation, capital G is a universal constant. In case of this K depends on the medium. This K depends on the medium. If two charges are placed in air, if two charges are placed in water, then the force between them would not be the same. The value that you see here is the most common value which works for vacuum or for air. It is in SI system, 9 into 10 to the power 9. So whether we have got a hydrogen atom, just a proton and an electron separated by nearly 10 to the power minus 10 meter distance, or a much more complicated system involving several point charges. We can handle all those cases. If there are multiple charges, then force on one charge net will be the vector sum of all other forces. It is just the simple vector concept in that case. While this is valid for point charge, we can prove this later on, that it is also valid for spherical charge distribution, spherical symmetrical charge distribution, whether that sphere is solid or hollow. So you can have two spherical balls, both solid. You can have two spherical hollow balls, or one solid, one hollow ball, one point charge, one solid ball, one point charge, one hollow ball. All combinations you can think of. As far as charge distribution is uniform in the ball or in the shell, this formula will still hold good. Remember gravitation. The formula G m1 m2 by r square That formula works for point masses. It works for solid masses, planets, stars. It also works for shells. Similar thing is valid here also. In this figure, what is the direction of force on proton by electron? Direction of force on proton by electron. Will it be towards the left? Will it be towards the right?
The right.
That's the
Right.
left.
Right. Why left? Electron will attract.
Sorry, yes, left. Sorry, right.
Right. So you can see that Newton's third law, that works here also. This formula for force is for both. For both. Force that this fellow experiences due to this. Force that this fellow experiences due to this. It is for both. And these forces are equal in magnitude, opposite in direction. Next question. There is a rod minus charge here plus charge here. It is insulated, so charges cannot move. One negative charge is placed here. Will this rod experience net force due to this towards the left side, towards the right side, or it will not experience any force because the charges are equal in magnitude. So the force will cancel out. If the question is not clear, let me know and I will explain it again.
So 0.
The left.
It's a rod which has left. It has got some finite length. This is a rod which has got some finite length. Now, if left is the answer, why is it so?
So because the distance between the minus and the plus charge is less. So force will be more towards the left.
Correct. Force of attraction, because distance is less, is more. Force of repulsion, because the distance is more, is less. The forces are not equal, so they will not cancel. I hope it is clear. Have a look at this and let me know if you have any questions. This is a pendulum. Its bob is uncharged, but it is metallic. It's a metallic ball which is not charged. This is also a metal ball which is connected to the ground. Metal ball which is connected to the ground. Basic idea of connecting to the ground is that ground can neutralize if you have got excess of positive charge, ground can supply negative charge. If you have got excess of negative charge, ground can take that negative charge. Technically speaking, ground makes the potential zero, but we have not talked about potential yet. So I'm trying to keep it simple by saying that positive fellow, if there, ground will send negative charge. If negative fellow is there, ground will accept that negative charge. That's the idea of connecting this ball to the ground. While it moves, it can touch this, it can touch this also. This fellow is charged. That is also metal ball which is charged. This is metal ball which is grounded. This is a metal ball also. This is insulating thread. No charge can flow out. It is released. It is released. Then what will happen? Nothing will happen. Because it has no charge, nothing will happen. Or it will go to the left and stick to it. It goes to the right, sticks to it, sticks to right ball, swings back and forth. Which is the correct option? Swings back and forth. That is option D. So which is correct? I can give you one hint if you want. When you want it, and if you want it, then raise your hand. And the hint is this. Closer and farther. Closer and farther. Electrons, just assume some charge here. Take it positive if you like. Electrons that are free, it's a metal ball, right? They will be interested in this side. They will come here. So that side will become positive. And if negative is close to positive, force here will be more than force here. So minus and plus will appear due to induction. Minus is closer, plus is farther. Attraction is more, repulsion is less. Now think further.
So the pendulum swings. So the pendulum swings.
It does, but what is the explanation? It is quite not very straight.
So when that metallic bob and sir,
yes, I noticed that
electrons
hand raising. Carry on.
Sir, the electrons present in the ground are attracted towards the positive charge present in the pendulum.
Well, you have to tell the whole story. That ground thing is not going to come yet. Force is more here, so it will go first to the left side. Question of ground is later. First, what will happen? Will it not go to the left side?
Yes, sir, it does.
So when it goes towards the left and attaches to the positive charged body, so there is an flow of electrons from that bob to that body, and so then after there is a net charge. So when there is a net charge in that bob is positive, and then it will feel a repulsion, and it will move towards
Very good.
So since that ground body is neutrally charged, and when it attaches to that ball, so there is an neutralization of charge, so which again forces it to.
That's quite good. So after this point, because of attraction, it attaches itself here, but then it is a conduction. Positive charge. This is still neutral, by the way. When it is touching it, it is still neutral. So now it is because of contact, conduction takes place. Positive charge jumps. Technically speaking, electrons would flow, but effectively speaking, we can say positive charge jumps. Positive charge jumps, but then repulsion starts taking place. Because positive charge jumps, repulsion starts taking place. So this fellow is pushed now to the right side. pushes, reaches here. Now it comes in contact with this fellow, but this fellow is connected to the ground, makes this body electrically neutral, zero charge. Zero charge, same story again, induction, pull, touching, conduction, repulsion, again touching, neutralization, again same story, same story, same story. Have a look at this explanation. Let's assume in this explanation that this is negative. So this is positive. Positive, negative. Attraction is more, repulsion is less. Since positive, this side is positive. Positive is closer, attraction is more. So it starts moving towards left. Like that. Look at the change in color. The moment it comes in contact, look at this change in color. It was negative, this takes negative charge. This is by conduction. And please note, earlier we talked about induction, but it is not full induction process. Full induction process involves grounding. So that induction was limited to charge separation, that's it. No transfer. But transfer is due to conduction, this point. Once they touch, both are negatively charged, repel. Due to repulsion, it goes, touches grounded sphere, becomes neutral again, this one. Become neutral again. After it becomes neutral, due to gravity, it will come to the left. This position, right? Let me use white light colors. So it becomes neutral. And just like gravity pendulum swings, it will swing. But there will be induction due to this. Whole process will repeat. So swings is the correct answer. If you have any questions, then let me know. Now I'm making one change to the question. This was conducting charge, this was conducting grounded, this was conducting neutral initially. I'm making it non-conducting. Insulator. That ball, say a rubber ball for example, doesn't have free electrons. These are conducting, no changes in these two. No changes in these two. Now what will be the answer? That is your assignment, and you must write some sentences need not be long to justify your choice. That's your assignment question. Any clarification? Let me know right now. You can submit the assignment from the usual place. We stop now.